Okay, so I just wanted to give a quick, before we get started with the actual material, quick overview of what we're going to do for the rest of the semester. Since we lost a week to COVID, and as of right now, they're not planning on giving us that week back, I'm going to change up the schedule a little bit. So we're going to finish up optimization today. We're going to talk about undefined behavior on Monday. We'll have another lab period for the optimization lab that you started working on yesterday. So hopefully that'll be enough time that you're not doing that too much outside of the lab period. And then we're just going to go straight into the back end of the compiler. So we'll do one lesson each on instruction selection, instruction scheduling, and register allocation. Selection/scheduling, maybe sort of, scheduling might bleed into this lecture a little bit. But we'll have to do a quick brush over each of those. And it looks like we do have time for one more lab. So I'm debating which one I want to do. We'll either work with PIN or Ghidra. So it'll be a slightly different system, but working with code at sort of a lower level, getting a sense of how you work with it in assembly code, and analyzing some stuff from the labs that we've looked at, or from the content we've looked at up to there. And then after that, we will basically have 2 weeks of project development time to work on something on the middle end or back end of the compiler. So that can be anything from basically extending the dynamic analysis lab that we did, where you inserted a hook at the beginning and end of a function, doing something with that. Extending the optimization lab, basically doing some other optimization on code, understanding how that works, or anything on the back end of the code where we'll talk about some of the projects that you can work on there. Basically, doing some sort of binary analysis instead of at the middle level, but that'll be the same as the the first project, which is teams of 1 to n, depending on what you want to work on, and I'll try to give you some time to work on that, or to form groups and things like that. So let me move this so it's clear that that is not the actual due date. So project 2 will be due at the end of the semester. This will sort of be up to all of you. If you want it to be due before exams start, we can have it due on the 28th. If you want to have it due after exams are starting, I think the academic calendar, I forget when exams go to, but technically spring term ends on the 28th, and you have review study days and then exam days up until the 7th. So we could have the project due as late as the 7th if you want the extra time. If you want it to be just done there, it can be due on the 28th. And I'll expect a little bit less than I did for the first project, since we won't have quite as much time, and there won't be as much ability to interact as there was with project 1. So I will be sort of looking for more of like a minor extension to one of the labs or something like that, not a full new project necessarily, because of the fact that, again, I know it's going to be harder for all of you to coordinate. It's harder for me to help you with the projects, all of that sort of stuff that we have to deal with due to being remote. So we can talk about that a little more as we get closer to that date. We still have a couple weeks till we're there, but I just wanted to give you a quick overview. So that's what we're going to do for the rest of the semester, due to the fact that we did lose that week to COVID, not having classes. So we're a little bit behind where I'd like to be. Any questions on that? Okay, cool. I'll probably try to cut that out of the video so that that's not there. So today we're going to be talking about global optimization and interprocedural optimization. And we'll be going through the data flow analysis that we use in global optimization. So due to the complexity, because we're looking at multiple basic blocks, we talked a little bit about local optimization, and the fact that we in local optimization have this nice property that basic blocks are executed sequentially. and all of the instructions are always executed. Once we move to global optimization, we no longer have that property for the optimization we're performing, because we have it for each individual basic block, but we have control flow. So since we do have control flow here, we need to assume that that control flow might change what happens in that function, depending on how the control flow works out. And so we need to do some analysis to figure out if it's okay to do this optimization or do an optimization. So what we're going to look at is what we call data flow analysis. And data flow analysis is very similar to control flow analysis. You're looking at a control flow graph. You're doing, some analysis of what the control flow could be. But the difference is that you're mainly focused on like what is happening with the variables in the program, what is happening with memory locations in the program. Whereas like control flow analysis, you're more so just concerned with where is the program going. So like, we talked about which nodes dominate other nodes in a control flow graph. That's just, we care about which basic block is going to get executed. But we don't necessarily care about, what variables are in those basic blocks at that time. So today we're going to consider an optimization that eliminates useless store instructions. This would be dead code elimination. Dead code being, store instructions that are now dead code. So this optimization has to be performed globally because we need to ensure that the stored value is not used later in the program. And we will talk about the fact that, you might think, well, we need to do this whole program because we need to make sure it's not used in the program, but we can do some local or some global analysis that checks to make sure that this is not going to be a whole program issue. We'll get to that a little later. So overall, what we want to do with this optimization is figure out when a stored value is not accessed by a load instruction that comes after the store instruction in program orders. So we want to make sure that if we store something and we load it later, we don't eliminate that because that means it's not dead code. But if we store something, we don't load it after that point, that it is dead code. So to do this, we need to analyze the instructions in the function to ensure that the store instruction is not followed by a load instruction. So we say that the term for this is a stored value is live out when it is used in a basic block without being redefined first. And we can define liveness of a stored value with the following equation. So just to break this down, I know this is a lot here. Live out for a basic block n is going to be based on the union of all of the successors of n in the control flow graph. So if we have a branch from a node in the control flow graph, a basic block going to another basic block, jumping to another basic block, we will look at all of the successors of that basic block, so all of the immediate successors. That means you have an outgoing edge from your basic block to another basic block. And we're going to look at its live out if it is used in a successor. So a variable is live out if it's used in a successor, or this union basically means that it's an or condition, since we're adding in anything from this set. So it's going to be live out if it's used in a successor basic block, or if it's live out of that successor block and it's not killed by that successor block. And kill here is essentially a substitute for defined by that basic block. So if we redefine the value of a variable in a basic block m that's a successor of our basic block, that means that it's not actually like the value that we stored in n is not going to be continuing to be used by the program after this point. So if we do a store in the first basic block, we restore a new value in the successor basic block, that kills the store that was done in the original basic block. And we'll do this as sort of I do have a slide here to go through this, so hopefully that'll become more clear as we go through. So again, the set used contains all of the stored values that are used in a basic block without being redefined. So that's, I am relying on a previous value that was stored in a previous basic block is the use set, which means that we needed that store that we did basically. And then the set kill is all the variables that are defined at M. If we negate the kill set, that's all of the variables that are not defined in M. So this condition here is basically it's live out of the basic block and it's not defined in that basic block. So someone else is defining it and someone else is using it is what we're saying there. So this union then gives us all the things that are used in our basic block or the things that are used in a future basic block. And when we look at all the successor blocks, that tells us what our successors, what the nodes after us are using, which lets us know, can we eliminate things in our own basic block, essentially. So we have to note that a value is live in a basic block if it is live on some path out of that basic block, not necessarily on all paths. So because we have this union, we are making sure that no matter what the control flow is in this program, we are going to know all of the things that are live out of that basic block. So this is an example of data flow analysis, by the way. There are a number of different forms of data flow analysis. If you look through the course textbook, or if you end up at some point, looking through the Dragon or Tiger books that are common in like grad compiler classes, you'll see equations that look like this for a number of different things like liveness, dominators, alias analysis, that sort of stuff. Like this is a common format for data flow analysis. It's just depending on what you're looking for, these sets might be computed in different ways. So we just want to do an example here to make sure you're familiar with how these equations work. So we're going to solve this and most other data flow analyses iteratively. So we will construct a control flow graph. We'll gather information about the basic blocks, so basically constructing the sets for the individual blocks without considering all of the other blocks. So we can figure out what is used and what is killed in each basic block without looking at the other basic blocks. And then we'll iterate, looking at the successors until the live out set does not change for any basic block. So this means that this is it will terminate eventually. We will always get this to terminate at some point, basically because there are a fixed number of variables used in a program, and there are a fixed number of basic blocks. So every time that we add a new basic block, or add a new variable to the live out set, like basically if it changes, if the live out set changes, that means we've increased some live out set by one variable. And we can only do that number of variables times number of basic blocks times before we end up with a full set for every basic block. So we will eventually terminate as we iterate through this, but it may take some number of iterations to sort of propagate from the end basic blocks to the beginning basic blocks, because we have to know if something was used in a successor, of a successor of a successor, that ends up propagating back to all of the predecessors to know that we can't eliminate that value. We can't eliminate that store. So let me share this with you in case you want to look at this separately. But otherwise, we're just basically going to do an example of this type of analysis. So here we have a set of basic blocks. So we have BB1, BB2, BB3, BB4. In BB1, we do a comparison based on a variable A. So I'm going to just highlight the variables here. We then jump and we define a new variable condition. We jump based on that condition to either BB2 or BB3. So this is an if statement. We're checking, integer comparison, equality, integer 32, A compared to 0. So we're checking to see, is the value of A 0? So this would be like incoming to a function. We'd have, maybe we can do the C code over here for this. So we would have void foo int A coming in, and we have if A is greater than 0, maybe. And then this is BB2 here. This is BB3. So the first basic block is the one that's doing the comparison. BB2 is doing B equals A plus 1. C equals A plus 2. I'm eliding some definitions of types here. And then BB3 is doing that. And then they all end up at BB4, which is the basic block after the divergence. We have a phi node here, which is getting the value of E from either A or B. So, you know, in reality, this, I guess, would be like B and D would be the same variable here in C code. Because we're getting that value, we're going to end up doing something with it here, and then we're saying F equals 5. That's roughly what our code would look like in C. This is sort of mashing up C code with SSA form, so this is not really a great format for this, just because we have this phi node here that's joining two things together, and that's tough to represent in C. But that's roughly what that would look like. So the first thing in our steps here is we are going to construct the control flow graph. So I'm actually just going to break this out into lines here. So we're going to construct the control flow graph, and then we're going to figure out what the initial information is for each of these basic blocks for used and kill, and then we're going to iterate and form the live out array. So our control flow graph is basically just going to be the basic blocks. We're going to have one node for each basic block in this system, and we're going to connect those nodes based on the control flow that we see here. So we're going to have BB1, BB2, BB3, and then BB4. And we know that, you know, our control flow graph should, you know, basically show that we have divergence from BB1 to BB2 or BB3. And then from there, we should go from the second basic blocks and the third basic block to the fourth basic block. So it should look roughly like this, right? Because we have this control flow divergence between these two nodes when we have this if statement. So basic block 1 can go to basic block 2 or basic block 3. Basic block 3 can go to basic block 4. Basic block 2 can go to basic block 4. And that's all the control flow in this program. So it's a pretty simple one. We may also want to know what the successors are of these nodes. So that's any successor in this data flow equation that we're looking at. So, you know, we're using this M in successors of N. So we might want to have a, you know, table that basically shows us, you know, what the successors are of each basic block. So, you know, if we have for each basic block, we don't have any successors for BB4, so we can show that as well. So we're going to have the successors of basic block 1 are BB2, BB3. Basic block 2 successors are BB4. Basic block 3 successors are BB4. Basic block 4 successors are null. So we have this information then so that, you know, we know in this equation, basic block 1 is going to look at and combine the values that we have for basic block 2 or basic block 3, because we can go to either one of these from the first node. And then we have the same thing for basic block 2. We're going to look at the values coming from basic block 4. For basic block 3, we're going to look at the values coming from basic block 4. For basic block 4, because this is a global analysis, we're only looking at this function. So we're not going to consider anything coming from other functions. However, we could do this as a whole program analysis, and then we would basically have, you know, what is coming out of this function, you know, where is that going to? what is coming into this function into BB1, or where are we calling this function from. We could extend the analysis to be whole program, but that's going to be a little bit more complicated, and we'd have to add in the call graph then so that we know, this function calls this function at this point, it returns to this function, etc. So we'd have to know the entire call chain that the program makes the call graph that it executes on. So this is our first step. We just build the control flow graph, and we want to know the successors of each node so that we can use that moving forward. So next, we have this control flow graph still here at the bottom. I just made it smaller on this slide. Next, what we want to do, our second step here, is to gather the initial information about the basic blocks independent of the other basic blocks, and figure out what is in the used and kill set for each basic block without considering the other ones. So we're just going to construct the used and the kill sets, and then the not kill set as well. So that way we can know what all of these values are when we try to do the live out version. And I'm going to steal, just copy and paste here from the completed slide real quick. So I have the null symbol. So first we need to know what is used in each basic block. So here we're just looking at the variables, and we are going to add in whatever variables are used here. I'm actually going to ignore the condition one because it's being used in a fee node, and it's not actually being defined anywhere else. So we're just going to sort of ignore it going forward, but we will say that it is defined here. So remember, the use set is what do we use without defining it, and then the kill set is what do we define whether or not we use it. So the use set for BB1 is going to be A, because we are using the value A in here, and we did not define the value A. So we don't have a left side that has an A on it, which means that we're getting this from somewhere else. So we know that, if we were doing a whole program analysis here, we would know that the value A actually has to be maintained from some other basic block or some other function. We can't eliminate a store to A because we are in fact passing that into this function. We're going to use it in this basic block. So BB2, we're going to do the same thing, which is that we end up using A without doing any store to A. So that because it's on the right hand side, we're going to put that in BB2's used set as well. So let me fix the fonts for these. Okay. BB3, same deal. We're just looking at the right hand side to see what is being used in this without being defined. And again, that's going to be A for BB3. And then BB4, we're going to look at and see what is being used here. So because we do have a fee node here that has con B and D, we are using the values B, comma D here. We are not going to consider this using con because this is sort of a fragment of the fee nodes that we have to basically in the SSA form, we want to keep in mind that we do have this condition that is affecting the values of B and D, but it's not actually being used as a variable in this basic block. Like condition will never show up as something that's in a register here. We're just keeping track of this for the sake of knowing that this value E could have come from D or B at this point. So we're saying that we use D and B and D. We're not using con, again, because it's part of the fee node and not part of the actual data flow. And then we are not defining anything, or not using anything as part of the definition of F. So we don't have anything else used there. So that should be our used set. It's just, again, the variables basically that are on the right-hand side of equations in that basic block. Any questions so far on how this is working? Okay, so moving on, we also need to define the kill set for each of these each of these basic blocks. So the kill set is the things that are defined within this basic block. So we want to know what values are being defined here. So for BB1, we are defining cond. We are defining a condition that may be used later on in this application. We don't end up actually using it anywhere, but it is something that is defined within this basic block. So it's basically on the left-hand side of the equation. Those are the things that are defined or killed by that basic block. So we use the term kill because it kills a prior definition. So, you know, if we had another line here that defined b equals, 5, this definition b equals a plus 1 would kill the prior definition. So it makes it no longer useful and eliminates it. So that's why we use that term here. So BB2, we're just looking at the things that are, again, defined within that block. So on the left-hand side in BB2, we have b equals a plus 1 and c equals a plus 2. So not too tricky. In BB2 or BB3, we define b. So we have b equals a plus 3. And then in BB4, we define e and f. Okay. And then we're going to compute the negation of this set of variables as the complement of that set of variables as the not kill or the complement kill set. So here we're taking the full set of variables, which is going to be, the full set is cond A, B, C, D, E, F. So we're going to take the full set and we're going to eliminate anything from the original kill set from that set. And that's what's going to be the complement of the kill set here. So we're basically saying what is not in this set that could be in this set. So here we'd have A, B, C, D, E, F for BB1. For BB2, we'd have anything that is not in the kill set. So cond A, E, A, C, E, F.
C's in the set, sir.
Oh, sorry, C's in the set. Thank you. A, D, E, F. Yeah, you're right. Thank you. And then cond A, B, C, E, F here, and then cond A, B, C, D, F, or A, B, C, D there. So we're just taking the the things that are in the kill set, eliminating those from the full set, and that's what's our complement of the kill set. So hopefully not too difficult. Okay. So I'm gonna just real quick duplicate this other slide again. Make sure that we eliminate these real quick. And hopefully this is the same thing. I think I did, just out of simplicity's sake, I eliminated cond from this set here, or these sets here. And actually this should have been A. It is used. I think I eliminated cond from the sets here just so that it wasn't confusing because we aren't using that outside of BB1. So that's the only thing I highlighted here was not having that cond variable sort of track through the rest of it. So we're going to ignore that for the sake of the fact that it's it's only really used in this phi condition. So we'll move on from there. So now this third step that we're going to do as part of iterative data flow is to iterate until the live out set doesn't change for any basic block. So we're going to start with an empty live out set for every basic block because of the fact that we don't know what's supposed to be in that set yet. And let me copy and paste this equation over to here. Not paste any of the symbols. Hold on a second. Okay, there we go. So we have this equation, which is what we're going to construct live out of each basic block based on. So we'll start with basic block 1 here. So live out for basic block 1 is going to be the union of the successors of basic block 1. So we're looking at basic block 2 and basic block 3 here because we are looking at M. So I'm just going to highlight those real quick. These are the ones that we are going to be looking at while we are considering the live out set for basic block 1. And then what we're going to do is we're going to compute for each of those successors the union of the use set with the live out set intersected with the kill set. So right now, what is the intersection of live out for basic block 2 with anything?
Nothing.
Nothing, right? So basic block 2's live out set is currently null. It's currently empty, which means that if we intersect it with a kill set, nothing's going to happen. So the first iteration of this is essentially just looking at the successors of each basic block and looking at the used set for each of these. So we don't even really have to consider the kill sets for the first iteration. We just have to consider the used sets. So we're essentially just going to say, okay, basic block 1 is going to be the union of all of its successors used sets. So the two successors are basic block 1 and basic block 2. Their used sets are both just A. So basic block 1 for iteration 1 is just going to be A. Let me just real quick here. So it's just going to be A for basic block 1 because we know that both of the successors have A. Then we can move on to basic block 2 and 3. So if we go back to the original colors here, basic block 2 and basic block 3, their successor is basic block 4. So they're both going to be the same for this first iteration. All we're going to do is we're going to look at the successors of basic block 2 and basic block 3, so the union of all of their successors. So the nice thing here is because it's a union, we can just sort of do these individually and then combine the results. So basic block 2, we're looking at basic block 4. We're only looking at the used set again because the live out is currently empty, and the intersection with the empty set is always going to just be the empty set again. So we have the successors are going to be the used set for basic block 4, which is B, comma D. You can see here that we don't actually have a successor for basic block 4. So because this is a global analysis, basic block 4's live out set is still just going to be the empty set. We don't have any used successors. We don't have any live out sets for successors. So this is always just going to be null. So basic block 4, because of the fact that we're doing this globally, all of its live outs are going to be the empty set. Okay. Any questions so far? Okay. So now we're just going to iterate. So now we move on. We're going to go back to the condition where we're looking at sets. We're looking at the successors of basic block 1 again. That's basic block 2 and basic block 3. So now we're going to look and see what is in the use set. That hasn't changed. So we've already included the use set. So now at this point, we're basically just looking at this second part of the equation. The use set is not going to change at all. We've already unioned that in. So now for the further iterations, we're really just looking at live out and live out intersected with the complement of the kill set. So we're looking at these two intersected with these. So here we're going to have for BB2, B and D intersected with A, D, E, F. So that is going to include one thing, right? the intersection of B and D with the A, D, E, F. The only thing that's the same in those two sets is D. So we're going to include D into A's new live out set. So it's basically saying that from basic block 1, someone is going to use a value D without defining it. And that's basic block 4 uses that value D without defining it. So we need to know that basically it is possible that this value D gets used if we go through this path where we don't define it. So it might be possible that we have, you know, an incoming value somewhere that if we did this as a whole program analysis, we would have to know that D does need to be defined and that store can't be eliminated. So this is really only useful here in the context of like a, you know, continuing this on going to whole program analysis there. So that's our intersection for BB2. Then we can do the intersection for BB3, which is B and D intersect with A, B, C, E, F. Since D is not in that set, but B is, we are going to include B in that set for A. And again, that means that B is defined by some basic, or B is used by some basic block used here, and it's not defined by BB3. So there is a path where we use that in BB4 that this does not get defined somewhere else. So it is live out of basic block 1 if there's no definition. So this basically just means that we have, you know, this case that we could skip this control flow. We could end up there. So that's basic block 1. Now we'll look at basic block 4. So this is the successor for these other two blocks. And we know what's going to happen here, which is that because of the fact that, again, the use set doesn't change, so the use set's going to stay the same. Basic block 4 has an empty live out set, and will always have an empty live out set in the global analysis. So when we intersect the empty set with its complement of the kill set, that's still going to be the empty set. So we're not going to add anything to BB2, and we're not going to add anything to BB3. Their sets are just going to stay the same. We are going to iterate one more time because of the fact that we do want to make sure that nothing is changing. We sort of know that because BB2 and BB3 didn't change, BB1 is not going to change this time. Since BB4 didn't change, BB2 and BB3 are not going to change. So now that we've iterated one more time, we didn't add anything to this, we're done. So now we have the live out sets for each of these. We know what variables are going to be used further on. And this actually shows us then that, you know, this should have been kind of obvious that we don't use this value C anywhere else. So this is dead code. We could eliminate that instruction C from the application and it would still be correct. So that's what this is trying to find, is basically, you know, where are things in this program that we can provably eliminate from that program and not change the outcome of the program. Okay. So any questions overall on how this works, or, you know, what's going on here? Okay, cool. So yeah, so that's an example of data flow analysis. I just wanted you to be kind of familiar with this because, you know, it is something that comes up in a lot of these analyses. You know, working on a project, you might decide to use something like this. I just want you to be familiar with this. So there are a couple big complications to this. Right here, we're making some assumptions, namely that these memory locations that we're storing to are not the same memory location. So we're assuming that there's no aliasing happening here. So we've talked about this a couple other times. I'm just going to gloss over it. So again, we know that an alias exists if there is more than one location, or the same location in memory is pointed to by two different pointers. So, you know, here we have X is a memory location on the stack. Y is a pointer that points to that memory location. So we can change the value of X either by referencing X itself or by doing star Y equals, you know, a new value. So both of these will change the same memory location, and that means that these are aliases. So for these types of computations, we need to ensure that the variables we're looking at here do not alias each other. If we have C as an alias of, if C is an alias of D, for example, that means that D is now actually part of the set for BB2 instead of C. And that means that C's, the store here, can't be eliminated because that is actually going to a different location in memory and is actually being used later on in the program. So we need to make sure that we don't have aliases when we do this type of analysis, because that can change the outcome of the analysis. We also have to consider that a global optimization only looks at code in a single function. So we also need to consider that other functions might affect the liveness of the stored value. So to basically, this is how we deal with the fact that a global optimization might affect the whole program. So we can be conservative here, and we can analyze whether or not a memory location escapes from the current function. So you'll see this termed as escape analysis. It just basically means that if we have a memory location that might leak from a function, we have to assume that that might be used later on in some other function. So these are things like global variables. Global variables can always escape from a function because they are, by definition, global. If it's a local variable, like something on the stack, then we have to take its address and put that either on the heap, so something that was mallocked or newed by a program, or into a global variable. So there are a number of ways for things to escape, or if we pass it as an argument to another function call, then we don't know what that function does with it. So there are a number of ways things can escape, and we basically have to be conservative and say, if a value escapes from this function, then we have to assume that it is being used later. So if we say that f escapes from this function, we would essentially add f to the use set for the end of the function, and then we would propagate that back to say that like f is live out of this function. So we would sort of have to define whether these things escape or not to determine whether or not they are live out of that function, whether or not we can eliminate that store. Because looking at this function, by itself, we could assume that we could eliminate f. We could actually assume that we can eliminate e and then eliminate the entire function altogether, right? Because we don't see any uses outside of here. So we need to know what escapes from this function in order to properly optimize it. And then finally, we have to consider the undefined behavior or the semantics of the language. And this is what we're going to look at over the weekend. So there's a blog post here. It's a 3-part blog post by the LLVM team. So this is your assignment for next Monday, is to read this. I'm going to put up a short reading quiz on it so that we're definitely able to talk about it, because I think it's very important to sort of understand. This will sort of talk about how how code is optimized based on the undefined behavior, based on the language semantics of C and C++. So I will link this, and I will send out the reading quiz shortly. So we'll talk about that next week, but we do have to sort of consider the undefined behavior. So let's kick off real quick. I think we might be able to finish this. If not, we'll finish it on Monday. So we want to talk about interprocedural optimization as well, which is local optimizations are performed on single basic blocks. We just talked about global optimizations performed on functions. Interprocedural are performed on the entire program. So interprocedural optimizations often make use of the call graph of the program, which shows how functions are called from other functions. And generally, these are more powerful, but they take a lot more time and resources to perform due to the need to analyze more code. So if you run things that have interprocedural optimizations, like you will notice a noticeable increase in runtime if you compile a bigger program with O1 versus O3, because -O3 is going to optimize with interprocedural optimizations. It's going to look at the entire program. it's going to take a lot longer to compile the code. So one of the common interprocedural optimizations is function inlining. This is sort of one of the biggest ones because it removes the code that calls a function. It moves the body of a function into the body of another function. So this allows us to remove code used to call the function, which is setting up arguments, doing the actual branch, and handling the return value. So we can basically take the body of the function, put it into the function we have, inline it somewhere, and then we can eliminate all this extra code that can be a substantial amount of performance to run that extra code. So for frequent calls to a small function, inlining can really improve the performance of the resolving code. So if we have like a loop that calls a function and that the function body is small, we can inline it and we don't have to do a call every single iteration of the loop. We don't have to adjust the stack every single iteration of the loop. So this can be a big performance gain if we inline properly. We don't have to consider whether values escape once we have a function inline because we see all of the inline code within this function. So inlining can make global optimization a bit more beneficial because it increases the scope of a single function, right? Now we have a single function that contains a bit more code. We have a little more room to optimize. So function inlining is a tricky optimization because there are a lot of different things that can determine whether it is profitable or not. So we talked about profit and risk. The profit of a function inlining is that we eliminate all of that function call code. The risk is that we might increase the code size. We might end up not lining up in the cache very well. We might only call that function once, and then is it really worth the risk of doing this? So we have to consider a lot of factors like callee size. So how big is the function that we're calling from? Is this already like a huge function that we're inlining even more code into? To the extent that we might push this out of the bounds of a few lines in the cache or outside of things like there have been hardware optimizations in the past where it's like a trace cache that tries to put all of the code into a small cache for loops. We might end up like going beyond the bounds of some hardware structure if we make our original function too big. Sorry, callee being the function that we're inlining. So how big is the function we're inlining? How big is the function that we're inlining it into already? How many times is it being called? Do we have any constant parameters that we can further optimize out? How many times statically is that function being called? So how big are we increasing the code size? How many parameters do we have to deal with? How many calls are there in the nested function? So do we have a complex thing that then we're going to end up wanting to inline more stuff in order to inline this original function? How nested is the loop? So are we getting a big gain because this is being sort of inlined in a loop that is being called a ton of times? And then how much of the execution time is this function actually taking up? So is this a big benefit where, this is 80% of the runtime of the program, and we can reduce that to, we can reduce that by 50% or something like that? Or is this, a 1% fraction of execution time function, and it doesn't really matter if we inline it or not? So there are a ton of different things to think about here. And this is where something like just-in-time compilation can optimize code better than a non-just-in-time compiler. So just-in-time compilers sort of profile your code as you run it, and then perform optimizations as the code runs. So this can sort of look at these factors as we run the program and then decide if it's going to be profitable or not. In a C or C++ application, however, we need to basically make this judgment up front and provide some heuristics basically to say, like, we're not going to inline functions that are bigger than this many instructions or that have multiple calls out of that function. Basically we can provide some heuristics that say when we will do this and when we won't. As a programmer, you can specify that you do want this to happen by using the inline keyword. Inline is it's sort of a suggestion to the compiler. So it may inline, it may not. but you can at least give it the idea that it probably should inline it, or that you would like it to be inlined by using this keyword. There's a way to force it. So there is another keyword called, it's an attribute, which is like always inline, that will force the compiler to inline it. So if you're very sure that you're more correct than the compiler, you can force that to happen. But generally, you would want to use inline and let it decide for you if it's actually going to be profitable or not. So let's stop there. Again, I will send out a reminder that you need to read this for Monday and answer some questions about it. That'll be your homework. And otherwise, I will see you next week. Have a good weekend.